And so getting information from the graph of a function. So we talked about the graph of a function over here. Should we look at some graphs? Yeah. Yeah. So, right. So here you have what I sometimes refer to as the menagerie, which is, what is a menagerie? You can always go and look it up, right? It's a French word, I think. And menagerie. Oh, I'm misspelling it. Menagerie. Form of, oh, menagerie. Menagerie. It's a collection of wild animals in cages or enclosures, especially one kept for exhibition, as in a zoological garden or a traveling show. Also, the place or building in which they are kept. Yes, indeed. So, can I get rid of the OED? Yeah. So here is a display of different kinds of, well, they're not animals, but they have behavior, right? So linear functions, well, a constant function is just a horizontal line. Linear function, you know all about these, right? Slope, intercept, point slope. The slope is the rate of change of y per change in x. The rise over the run. Okay, power functions, you got your second degree, third degree, fourth degree, fifth degree, and you see that the even degrees have y-axis symmetry. And I'm mousing over this here, but okay. I guess if I mouse, get a little confused as to where my mouse is sometimes. Yeah, okay. So you see the square and the fourth power, they look very similar, but the fourth power flatter on the bottom, steeper on the sides, right? Cubed and the fifth power look kind of similar, but again, the fifth power is sort of more extreme, flatter where it passes through the origin and steeper on the sides. Okay, so those are your power functions, and they continue on in that fashion, right? X to the sixth is even more extreme than x to the fourth, flatter and steeper, right? And x to the seventh looks a lot like this. And let's see, I see there's some chat here. Oh, Jasmine came in and so did Gail. All right, let me make a note of that. Williams and Salgado. Gotcha. And let's save that and put it in a lockbox at the bottom of the sea. So root functions, you got your square root, the domain is restricted. Your cube root, the domain is not restricted, right? Because you can take an odd root of a negative number, right? -1 cubed is in fact -1. So the cube root of -1 is -1. The cube root of -8 is -2, and so forth, right? So the domain of an odd root function is all real numbers. The domain of an even root function is just non-negative numbers, right? Reciprocal functions, 1 over x, 1 over x squared, 1 over x cubed, 1 over x to the fourth, right? So you see that kind of alternating even odd behavior again, right? Absolute value, step function. So yeah, the power functions include, the quadratic, which yeah, that's sort of a biggie, right? And we'll be talking about, but let's talking about that. Let's get in here and look at some exercises. Can I close this? So on the side, you see we have, the walkthrough of chapter 2. So the average rate of change of a function, linear functions and models. And we want to kind of move right on to transformations of function. I'm going to assume that linear functions are fairly well known, so I'll just sort of gloss over those. hitting the key points, right? But yeah, so when you make a table of values, you have a column for the inputs, right? So here you see the inputs. Well, can we close this out so we can maybe make this larger? Because as it is, it's too small. Okay. All right. So if you have a function, oftentimes we make a table of values, right? So you have a column for the input and a column for the output. And usually we don't have a separate column for the XY pairs, right? Because you've already got them here, right? Y is just f of x. So this column you got x and this column you got y. If you wanted to, you could make another column for the points, right? That those input output represent in the coordinate plane. So if f of 4 equals 10, for instance, then the point 410 is on the graph of f, right? If the point 37 is on the graph of f, then f of 3 must be 7. I hope that makes good sense for you. Yeah, oh, and Tia is here now. Let me make a note of that as well. Welcome. And okay, so we have here match the function with its graph. Well, you got 4 here, right? This is your square root function. This is your cube function. This is your absolute value function. And this is your x squared, right? Basic generic parabola. Okay, so we go over to the second column. Graphing piecewise functions. Yeah, let's pick one of these. How about 40? So for 40, you see that we have a different rule depending on where the input is, right? So if the input is less than -1, then the output is just -1. If the input is between -1 and 1, including -1 and 1, then the output is on the line y equals x. And if the output is bigger than 1, then we use this rule, which is that the output is simply the constant 1. So we're going to have a horizontal line up to -1, then we're going to have a line with slope 1 through the origin between -1 and 1, and then another horizontal line, y equals 1 for x greater than 1. And let me show you how to do that. I think we did this last time, didn't we? I can never remember what we have or haven't done. But if we go to the GeoGebra window, I can show you how to enter that in, okay? So we're going to say if x is less than -1, then the output is -1, right? Otherwise, if the output is between -1 and I guess there's an equal, less than or equal to x greater than or equal to -1 or -1 less than or equal to x, which is less than or equal to 1, then we're going to use x, all right? Otherwise, we're going to use, I think I can put this here, just 1. Uh-oh, nope. Otherwise, 1, like that. Oh, yeah, okay. So that's done it. And let me press enter. Notice the way it writes it a nice pretty type, right? So the same sort of thing we saw, right? So the rule here, and instead of the word if, they have a colon, right? So the output of the function is -1 if x is less than -1. Can we see the graph of that more betterly? Yeah, okay. So you see we have an output of -1. Notice that it's an unbroken curve, even though the rules jump around. The graph itself, there's no break in the graph, right? It takes up where it left off and goes up, and then when we get to greater than 1, then we level off to just 1. Right? Should we look at the rule for that again? Yeah. In fact, let me copy that. Can I copy that there? Oh, here. I'm I don't get a copy thing. Can I put it in the chat? Yeah. Oh, except I want to send that to everybody. Sorry, my Wi-Fi has been off and on. Okay. Sorry about that. Okay, I'm going to send this to everybody, and you can see it. I wrote in the chat what the function definition is. So you can see if x is less than -1, then you use -1. Otherwise, and then I have another condition, if x is between -1 and 1, use x, and then comma, otherwise use 1, right? So that's the syntax for these conditional piecewise defined functions, right? Conditional because the formula for the output is dependent upon where you are on the input. Okay. So let's move on. What are we looking at here? I don't know. We got 2 columns of stuff. Oh yeah, here's more piecewise functions, right? So we look at 46, try to write that one in. So what do we got here? We got a linear function, slope -1 for x less than 0. Oh, I'm not showing the right thing. Sorry. Need to turn off GeoGebra. Okay, so back in the book. So we've got a linear function with intercept 0, y-intercept 0, right? And slope -1. For x less than or equal to 0, that's what we use. If we go to greater than 0, then we jump from 0 up to 9, right? So that's a break in the graph. So let me try to draw this in GeoGebra. Let's see, can I choose GeoGebra? Yes. And then I want, oh, I didn't mean to do that. I just made it full screen, which meant, oh dear. Why did it go full screen? Exit full screen, okay. I wanted to go here and edit this thing, right? Okay, I have to be careful where I'm clicking around in here. So I've got the rule that says it's going to be -x on that interval. And then if we're between, sorry, less than 0. And otherwise, if we're between 0, and this should be less than or equal to 0. And this should be strictly greater than 0 and less than or equal to 3. For that, we're going to use 9 minus x squared. Otherwise, we're going to use x minus 3. Okay, so I've got something going on here. What have I got going on? Let's zoom out, right? Okay. So does that seem reasonable? This is a line with slope -1, right? Up to, but not including, oh, yeah, and including 0, right? So I'm going to put a filled in dot there. Oh, I need to, sorry, use the right thing. So the filled in dot there, right? Then I want to put an open dot around this point 9 on the y-axis. And the way I'm going to do that is by typing the word circle. And it says, okay, you want to circle, where do you want to center it? Well, I want to center it at 0, 9. And then, well, what would you like the radius to be? Well, comma 1, that's too big. How about 0.4? Yeah, that's a little bit too big still, isn't it? 0.3. Okay, that seems to be about the right size to convey what I want to convey, which is that the function does not have an output of 9 when x is 0, right? it has an output of 0 when x is 0, because we use this first rule, which is negative x, and if x is 0, negative 0 is 0, right? So that's where we are. For the input 0, we have the output 0, and then it immediately jumps up. It's like, so if this was like a graph of your position in space over time, then you would disappear at time 0 and reappear 9 units away somewhere, right? So, you know, this would violate the laws of physics, because that just doesn't happen, right? And then we have, we're on this parabola, 9 minus x squared, right? It's got a vertex here at 9, and it drops down to 0 when x equals 3, at which point we jump to the line y equals x minus 3, which is rising at a rate of 1 per 1, and has a y-intercept of negative 3. But it doesn't actually make that y-intercept, right? Because its rule doesn't kick in until you get to here, right? But if you were to extend this, it would hit negative 3 on the y-axis. All right, any questions about that? Is that okay? So yeah, piecewise functions, you can make it do all kinds of crazy hoops and jumps, and yeah. Okay, so we've been doing this graphing, finding piecewise functions. Oh, I'm sorry, I should be jumping to the text, which is here. Okay, we're not looking at the text because we've got GeoGebra. Finding piecewise defined functions. A graph of a piecewise defined function is given. Find a formula. Oh, so go for it. So this is, you know, what we're kind of into here, I think, as I mentioned, the rule of 3 before. For any mathematical relationship, you can view it numerically through like a table of values. You can view it graphically, as is done here, or you can view it algebraically through formulas. And given one, you can always get the other two, right? So here, given the graph, we could make a table of values by saying, look, when the input is negative 3, the output is negative 2. When the input is negative 2, the output is negative 2. Then you start rising up here, right? When the input is negative 1, the output is negative 1. When the input is 0, the output is 0. You could tabulate those as, you know, a table of x and y corresponding values. Here they want actually to fill in, you know, some kind of a formula. So what's the formula for x less than negative 2? Looks like negative 2, huh? Yeah, that's y equals negative 2 on that little stretch. And then the formula between negative 2 and 2, that looks like y equals x, right? The line with slope 1 through the origin. And then greater than 2, we're on this little horizontal stretch where y equals 2. Okay. And they, you know, we'll try some of these other ones. The vertical line test. So you recall the definition for a function and the importance of the word unique. So you have to phrase it correctly. So if I say for every input, there is a unique output, what does that mean? Well, what it means for the table is that, you know, if you have the same input appear twice in the input column, you should definitely have the same output corresponding to that input, right? So, you know, if today f of 2 is equal to 3, well, tomorrow f of 2 can't be 4, right? F of, you know, if it's the same function, it's got to have only one output for each input, at most one, right? It could be that there is no output because the function is not defined there. So we say for each input, there's at most one output. You can't have more than one. So that, and then for the in terms of the graph, that means that if y, the output variable y, is a function of the input variable x, then for each x, there can be at most one y, which is true on this graph, but not true on this graph, right? You see, if, you know, there's a little x somewhere in here, then there are going to be two y's, which if I had my stylus, I would draw on top of here the vertical line. Yeah, I know there's a whiteboard. I don't get the whiteboard because I use this OBS, and so I guess they don't let me have the whiteboard. I will eventually find my stylus. And equations that define functions. Okay, so here we don't have y as a function of x. Is y a function of x? Well, we could solve for y, right? This is a linear relationship. 3x minus 5y equals 7. And if we were to solve for y, would we get a function formula? Well, let's give it a whirl. And for that purpose, we'll go to pencil and paper. The pencil and the paper, they would come together on the DocuCam. Well, it's a Sharpie in paper. So if you have 3x minus 5y, I'm just copying the number. This is 2.2, I think is the section we're on. Number 57. We got to get a move on here, huh? Equals 7. This is a linear relationship. How can you tell? Well, there's no weird powers on x or y, right? The powers are just 1. And there's no roots. There's no absolute value. It's just a multiple of x plus a multiple of y. Well, minus, right? Plus negative 5 times y. That's plus a multiple of y equals a constant, right? So if we solve for y, what happens? Well, I guess we use the addition property or subtraction property of equality, subtract the same thing from both sides, and we want to isolate the term involving y, so we subtract 3x from both sides, right? And then we divide both sides by negative 5. And negative 7 divided by negative 5 is negative 7/5. And a negative divided by a negative is a positive, so I'm going to write that as 3/5 times x. All right, so that means that when x is 0, we're starting at negative 7/5. Y is starting at negative 7/5, right? So we can make a table of values for this, right? And so we could say, yeah, we start at negative 7/5, and then we follow a slope of 3/5, right? So the rate of change in output per change in input is 3 to 5. All right, so for every increase of 1 in x, we have an increase in 3/5 of y. So if I increase x by 1, I want to add 3/5 to this, I'll get negative 4/5, right? And if I keep adding 1 to x, I'm going to keep adding 3/5 to y, right? And get a table of values like that. So steady increments in x produce steady increments in y, and the rate of change in y per change in x is 3/5. Okay, so if I want to plot these points, looks like we got a lot of negative values here, so I'm going to sort of emphasize the third and fourth quadrants in my graph. And we're going 0, 1, 2, 3, I guess, right? So I'm going to make my x-axis and y-axis emphasize the fourth quadrant here. The quadrants go 1, 2, 3, and 4, right? Oftentimes denoted with Roman numerals. So you go sort of counterclockwise, starting in the upper right. So first quadrant, second quadrant, where x is negative but y is positive. Third quadrant, x and y are both negative. Fourth quadrant, x is positive, y is negative, right? So I guess I want to kind of count by fifths here. So I'm going to say here's 1, 2, 3, 4, 5/5. That takes me to negative 1. And another 1, 2, 3, 4, 5/5 takes me to negative 2. And I start here at negative 7/5. and I'm going to go up 3/5 for every increase in 1. So how shall I scale my x-axis? Basically, you want to choose a scale that will capture where the action is, right? So I'm going 1, 2, 3 here. So if I say, I could use the same scale on the y-axis, right? So I have 1, 2, 3, 4, 5 little, I've got graph paper here, right? So I can count 5, another 5, and another 5 little, are those centimeters? I think they're, yeah. Is this centimeter graph paper? They look smaller than centimeters, don't they? Oh, I have a little measuring thing here. So I just need to line this up. Yeah, it looks like ½ centimeters. Yeah, that makes sense, right? So this is 1, 2, 3 on the x-axis. Notice I've labeled my axes. That's important. Is it always x and y? No, right? Sometimes the horizontal axis is time and you put a t there. And sometimes the vertical axis can be u, v, or w. You can even have x on the vertical axis, right? So how do you know what it is? By the label, right? Okay, so here we're starting at -7/5. So we plot this 1, -4/5, that's here, right? And 2, -1/5, that's here. And 3, +2/5, that's here. And we notice that these points line up on a straight line. That's why we call it a linear relationship, right? And what's the function? Well, this is our function formula, right? We call this f of x. Or we could call it f of x. I suppose you could also call it g of x or h of x. But, you know, if the function name is f, then that's what we'd call it. And this would be the formula for that function. After we solve for y, we get a formula for f of x. And we see that that's a linear function. And yeah, you also see that, you know, we're following sort of this steady thing where we go over 1 and up 3/5, right? And then over another one and up another 3/5. Over another one and up another 3/5. So you got this steady rate of increase as we go along a straight line. Should we pick another one of these? How about x equals y cubed? This is number 67. X equals y cubed. All right. So do we have y as a function of x? No. We do have x as a function of y. Is that okay? Sure. So we could call this, you know, f of y. X equals f of y. That's perfectly okay. If you want y as a function of x, can we solve for y here? Yeah, what do you use to solve for y? If y cubed equals x, then y is the cube root of x. That's what it means to be. So this is exactly equivalent to saying y is the cube root of x. Right, and this is the cube root notation, a little radical with the index of what the root is, right? We could make a table of values, right? And again, so you're seeing that rule of 3 in play. We saw the rule of 3 up here, right? We had a formula, that's the algebra. We have a numerical table, that's sort of arithmetic, if you like. And we have a visual representation of this relationship from the table and the formula, which is, you can kind of think of this as geometry, right? And that was sort of the you know, the Renaissance, where René Descartes, the French philosopher back in the 17th century, I think, was reading disparate books from, you know, the Arabic culture, from Greek culture, and kind of putting them together and saying, look, we can, you know, have this wonderful playground of the coordinate plane, sometimes called the Cartesian coordinate plane. Yeah, so maybe I should write his name down here. Rene Descartes, where, you know, it's French, so there's some silent S's in there. Descartes, right? And what's he famous for saying? Anybody know his most notorious quote? Yeah.
No, sir.
Okay. Well, let me give you the Latin. We'll start with the Latin, okay? Cogito ergo sum. Yeah. Which means I think. Maybe you recognize this. Therefore, I am. So why is that so famous? Well, you know, in the Renaissance, there was a sort of a crisis of identity. Humanity was undergoing a crisis. Philosophy was undergoing a crisis of identity. You know, how do you know you really exist? You could just be the figment of imagination of some, you know, alien space creature on the planet Pluto, right? And Descartes' justification was, I think, therefore I am. Does that resolve it for you? I don't know. It doesn't really work for me. But yeah, it was an existential crisis, which was somewhat alleviated by this statement. Okay. Also famous for saying, don't put Descartes before the horse, because that would be wrong. Okay, so we're back to number 67 here. So we're working this, you know, playground of the rule of three, right? You got an algebraic formula, you got a table of values, and you've got a graph, right? So is there any restriction as to what x can be here? No, x is the cube of some number, which, you know, you can get any number by cubing some other number. Maybe that's not obvious. So the thing is that if y is negative, then so is x, right? The cube of a negative number is a negative number. So we don't have the same restriction we have with the square root, right? The square of any number is positive. With cube roots, the cube of a negative is a negative, right? 3 negative factors will give you a negative. Okay, so if x is, for instance, well, let's put in some cubes, right, for x. So if x is negative 27, well, that's, you know, if you look at this first equation, what do you cube to get negative 27? You cube negative 3, right? Negative 3 times negative 3 times negative 3. So in fact, the cube root of negative 27 is negative 3, right? Negative 8 is the next sort of perfect cube, and that's the cube of negative 2. Negative 1 is the cube of negative 1. 0 is the cube of 1. And all of these could be positive or negative, right? So we could just put a little plus or minus sign here and say, yeah, we got like a twofers for all of those. So how do we make the graph? Well, I think we're going to center the graph at on the origin, right? And maybe we don't want to accommodate that negative 27, right? Because it's kind of too far afield. We would like to say 1, 2, 3. Okay, so let's say here's 1, 2, 3, 1. These are perfectly evenly spaced hash marks because I have this ½ centimeter graph paper that helps me to make them perfectly evenly spaced. And then we want, I think, can we get out to 8, 2, 3, 4, 5? I think maybe. Let's see, 1, 2, 3, 4, 5. Uh-oh. Well, that would be 8, right? And back this way, we're also going to have trouble, right? 1, 2, 3, 4, 5, 6, 7. Yeah, that's going to be off the map, right? But we'll have an idea. So negative 1, 0, 0, 1, 1, and 8, 2, right? So we're all the way over here. Yeah. So how do we connect the dots here? This is like when you, this is practice for joining the FBI. That's what they do. Connect the dots. Well, we want a smooth, unbroken curve, right? Is a straight line going to do it? No, if I line up these two dots, clearly I'm going to miss the other dots, right? If I line up these two, I'm going to miss that one, or these two, right? So it's not a straight line. And in fact, we know what kind of shape it is because we looked at it before, right? It was in one of the standard shapes. So it comes, well, actually, can we plot this -8 here? 6, 7, I think it's actually here, right? Comes up here fairly smooth, and then rises up pretty steeply right there, and then comes out like that. That's a pretty crappy graph, but you get the idea. And it's got what's called origin symmetry. So for each point here, which is, say, if the input is A, then the output is A cubed, right? Then we have its opposite over here, right? 1, 2, 3. So right about here would be the point. If the input is -A, then the output is -A cubed, right? And if I were to connect the dots here, let me do it in pencil, see a line through the origin. Right? This is not part of the graph. I'm just sort of showing, yeah, that's sort of demonstrating this origin symmetry. So you take this point, reflect it through the origin. So go to the origin and then go the same distance on the other side of the origin. These are congruent line segments, right? That's a special kind of symmetry. Okay, so there it is, like the algebraic formula, the table of values, and the graph. You can kind of always work this with a mathematical relationship of this type, right? Okay, so let's go back to the text. Not seeing any questions in the chat, so I guess we're good. Oh, that's not what I want. I want this. And yeah, they have some postage rates and taxi cab function, and you know, in the interest of time, I'm just going to blast into the next section. Yeah, okay. Getting information from this is 2.3. So what are the topics here? Values of a function, domain and range, comparing. Can I do this? Whoops, I didn't mean to do that. I don't know what happened there. Can I close this thing? This is the problem with Adobe. Okay, yeah, I can. Okay, yeah, comparing function values, solving equations. Okay. And inequalities graphically. Okay, so solving equations and inequalities graphically. That's a good thing to be able to do. Increasing and decreasing functions. So when we say increasing, we mean going up to the right. So if your curve is heading up to the right, then it's increasing. If it's heading down to the right, then it's decreasing. Local max and minimum values of a function. Yeah, and I kind of, so I think, have we already talked about domain and range? The domain is the set of all inputs. The range is the set of all outputs. I think we have talked about that. So let's move on to where the exercises are. You know, domain and range from the graph. Yeah. So you see project onto the x-axis, you get the domain. Project onto the y-axis, you got the range. Comparing function values, solving equations, and inequalities graphically. So you can see from the graph here that if you're solving the inequality f less than g, then you'd want to find out where is f equal to g, and then test to see, is it in between, is it less than or greater than, right? And so the f is less than g on the interval from a to b, right? So they have some examples of that. I think maybe we should just go straight to the exercises, right? And increasing and decreasing. Yeah, we talked about this. Is kind of obvious enough, I think. The obvious is the enemy of the true, said a voice. Yeah, so they're showing, how to use graphing technology here, which we have GeoGebra for that, right? Local minimum max, right? So here, these are local maxima, and these are local minima. So if it's the lowest point in the neighborhood, then it's a local minima. If it's the highest point in the neighborhood, then it's a local maximum. Okay, so I just kind of want to have an excuse for fleshing out these ideas by every graph tells a story. All right, that looks interesting. And from the graph, we can get all kinds of good information, right? That it's not necessarily obvious from the formula or from a table even, right? So I kind of want to skip on to the domain and range. Okay, so if you have a linear function, then the domain and range are all real numbers, right? Provided it's not a horizontal line, that's technically linear, in which case the range is just that one value, right? The domain is all real numbers, but the range will just have one value in it. If it has any non-zero slope, like here 2 is a slope, then it's going to be the domain and range are both all real numbers. However, you can restrict it arbitrarily, just by edict, right? I am the author of this function, and I hereby declare that my inputs can only be between -2 and 5, in which case, even though the formula may accept other values, you've restricted the domain. So they're finding them graphically. Square root of x minus 1, that you don't really need a graph to find the domain here. You just write the inequality x minus 1 must be non-negative, right? So greater than or equal to 0, which means x must be greater than or equal to 1. Here, x must be greater than or equal to -2, right? Okay, I'm going on to the next page of problems. When is it sort of advised to solve graphically? Well, all of these, I think, are ones that you could solve easily algebraically. So let me see, do they have one here? Yeah, so some of these, not so much, right? Like this one, here you got not a quadratic, but a cubic. So that can be tough, right? So let's see how far I get, without using technology. They've got a little picture of a calculator here, right? So that's an indication that they suggest, yeah, technology might be helpful here. But oftentimes you can get, at least a certain ways along without the technology. So let's try number 20. Well, how about 28? Okay. So let's go to pencil and paper first. There we go. Pencil and paper. Here we come. And how are we doing? Got 11:50, huh? So we have the inequality. So this is 2.3, number 28. And solve the equations, solve the inequality. And you may need technology. Well, I mean, paper and pencil is technology. So by technology, I mean, electronic computing. So part A, they have the inequality 5x squared minus x cubed. Okay, so that's a little warning, x cubed, danger. And that's equal. Oh, well, they have first equals, okay, and then they say less than or equal. Okay, so equals negative x squared plus 3x plus 4. So when I categorize this inequality, I'm going to say it's a cubic inequality because that's the highest. These are polynomials, and the highest degree of any term on either side is 3. And typically what I want to do is, get 0 on one side, right? Does it matter which side? No. Let's add x cubed to both sides and subtract 5x squared from both sides, right? So yeah, I'll indicate that this way. So I'm doing the same thing to both sides, right? And when I do that here, I'm just going to get a 0, right? Over here, I'm going to get the highest term is x cubed, highest power term. Then I've got negative x squared minus 5x squared. Those combine. I've got, and just copying down the other terms. So that gives me cubic and descending powers, and I'm now comparing with 0. I like 0. In particular, if we can factor this cubic, now that's generally speaking a difficult problem, especially for a cubic like this with all 4 terms. Can we factor that? Nah. Well, if we can find a 0, we can factor it. By a 0, I mean an input that makes the output equal to 0. Is there an obvious 0? What if x is 0? Well, then you got 4, right? If x is 1, you've got negative 5 plus 7 is 2. So we go from 1 to 2, sorry, 4 down to 2. So should we tabulate these? So if we're thinking of this as f of x, or we can just call it y, I guess. This, yeah, so we're thinking of this as equal to y. Then if the input is 0, the output is 4. That's 0 plus 0 plus 0 plus 4, right? If the input is 1, we said it went down to 2. Is that correct? Yeah, negative 5 plus 7. How about at 2? We got 8 minus 24 is negative 16. Plus 6 is negative 10. Plus 4 is negative 6. Aha. And why do I say aha? The output went from being positive to being negative. The graph of a polynomial like this is a smooth, unbroken curve. So if you're going to go from a positive y to a negative y on a smooth, unbroken curve, well, let's go ahead and plot these points, all right? So we're doing it graphically, all right? So I've got positive inputs and both positive and negative outputs. I'm going to make a graph something like this. How about here? All right, and so we'll call this 1, 2, 3, 4. That's our, this is the y-axis, this is the x. Don't forget to label your axes. So 0, I'm going to say here's 1, 2, 3, perfectly evenly spaced hash marks. So 1, 2 is here, and 2, negative 6, 2, 4, negative 6, I think is here. So 2, negative 6 is going to be this point here, right? So I need to connect those points. I have to satisfy the vertical, sorry, these points. I have to satisfy the vertical line test, which means I can't zigzag back and forth, right? For each x, there can be only one y. And I want a nice smooth curve going from here to here. What does that mean? That somewhere in here, it's got to cross the x-axis, right? And that's where y is 0. That's going to be our solution, right? So I want to zero in on, that's where the expression comes from, zero in on this 0, right? What value of x will make y0. And maybe 1.2, you want to guess 1.2? It's going to be hard to plug in, right? What's 1.2 cubed minus 6 times 1.2 squared plus 3 times 1.2 plus 4. Is that close to 0? Well, what's 1.2 cubed? Well, 1.2 squared is 1.44, right? So we do a little side computation here. 288,144. So this is 1728 with a decimal point there, right? So 1.728. And this is 6 times 1.44, which is 6 times 4 is 24. Carry the 2, 26. Carry the 2, 6. And 2 is 8. Yeah, I think that's about right. I think it should be exactly right, right? Plus 3.6 plus 4. So how do we add these up? Let's see. Sometimes it makes sense to add 2 more. So let's add the positive values. And then we'll see, is that close to 8.6, right? So that then we could be close to 0 because we're subtracting 8.6, right? So this is 7.6 over here. Oh, there's going to be like 9.328 minus 8.64. And that's going to be, well, less than 1, right? Positive, but less than 1. Let's see, so 8 minus 0 is 8. 12 minus 4 is 8. 12 minus 6 is 6. And 0, right? So I think, yeah, 0.688. 688 thousandths. Which, you know, so where is that on? It's going to be just, you know, a little bit above, right about there, right? So we're close to the 0. Could we get closer? Yeah, probably by going like 1.25, right? Let's go ahead and use GeoGebra, a little technology now. I think we've earned the right by doing this much pencil and paper technology. Okay. So let's get rid of, this guy here. I need the pointer tool. Point to this. Hello? It's not going to let me point to it. Okay, I'll just turn it off then. I don't know why it doesn't let me select it. Looks like a bug in the software. But so what do we have? We've got 5x squared. Oh, sorry, no, it's x cubed. You notice that it starts to plot things. There's your cubic shape, right? You recognize that, x cubed? Okay, so what happens when I subtract 6x squared from that? Oh, well, you see that suddenly we have a 0 here, right? Okay, but we're not done. We need to add 3x to that. Okay, so that kind of moves things around a little bit, and then plus 4 is going to shift the whole thing up 4 units, right? So we get this shape here. Can we, oh, I don't want the point tool. Oh, that's what I thought I still had the point tool. Yeah, so we see actually there are 3 zeros to this thing. And we found this one, which was close. So, you know, we could continue our guess and check game, right? And say f, what's f of, what do we say? 1.25. And we, oh, I think I pressed the wrong thing. I think now that I can delete this, I want to, and this. So what did I say? One f of 1.25. That should be close to 0, right? Oh, yeah, it doesn't know f, right? The name of the function is here is g. And we see that that's a smaller positive value. Okay. You see that's, we had 0.688, it's at 1.2. So maybe 1.3, let's go all the way to 1.3. Okay, so g of 1.3, that's negative. Pretty darn close to 0 though, right? So something to the left of that, like g of 1.29. Let's try that. That's positive, right? Also very small. So maybe halfway between 1.29 and 1.3, which would be 1.295. That's negative, but look how small it is, right? It's like an order of magnitude smaller than what we had before. So I'd want to go farther to the left, right? Say g of 1.294. Okay, that's positive and small. And so we could keep, refining our guess, or we could do this, which I know this is kind of cheesy, but this works, right? We can just sort of point at that spot and say, oh, you want that intercept? I'll tell you what it is. It's 1.29428033603 to do 10 decimal places, right? And that's where the output is 0. But notice we got a couple other ones, right? So in general, a cubic will have 3 zeros. Now, I think what the book may have wanted you to do was take the left side of the equation, which is 5x squared minus x cubed as one function, and take the right side of the equation, negative x squared plus 3x plus 4 as the other side of the equation, and then see, where do those two things line up? Well, right here is the one we were sort of looking at, right? So if I say, well, show me the coordinates of this point of intersection here. I want a point. Got the point tool. And notice that it's 1.294. It's the same number, right? So now suppose we were saying, okay, what are the names of these functions? We've got the left side is f of x, and the right side is h of x. So in the book, they ask us to solve the inequality, right? That the 5x squared minus x cubed is less than this other thing, right? So in GeoGebra, if we're going to the technology, right, we can say, well, that's saying that f of x is less than h of x. Oh, that's g of x, h of x. And yeah, GeoGebra is pretty friendly about that, right? It says, yeah, here are the intervals where that's true. I don't want a point tool. I want to move this thing around. Here are the intervals where that's true, right? The gray curve is below the reddish brown curve on this interval, and again on that interval, right? And so the blue zones here are where that inequality is true. How are we doing? It's 12:05. Are we getting done with 12.3? Let's hope so, because at this rate, we're going to be here forever. I guess I want the book, and increasing and decreasing. How about max and min? Do we have some of those problems over here? Local max and min, right? So for a cubic, that's a difficult problem. That's really kind of a calculus problem. Except if you're using a graphing calculator, and they do suggest here, right, a graphing calculator. But you should know that this, finding the local max and local min for a cubic, generally difficult. and also for higher order polynomials. So these are all sort of higher order polynomials, right? This one, however, you can do without a calculator. So let me argue on number 54 with paper and pencil. So we want to find local max and min for it. We have just enough time maybe to do this. So here is paper and pencil, okay? And my function is a reciprocal of a parabola or a quadratic, right? So this is 2.3, number 54. And find extrema, that's local max and min for, that's plural of extremes, right, extrema. For v of x is 1 over x squared plus x plus 1. Okay, so, as always, you can always get in here and, make some table of values, right? Input, output, right? X is the input, Y is the output, V of X equals Y. And, maybe just round up the usual suspects near 0. See what happens to them. So if the input is -2, this is 4 minus 2 is 2 plus 1 is 3, that's 1/3. If the input is -1, 1 minus 1 plus 1 is 1. The reciprocal of 1 is 1. At 0, again, we got 1, right? Does that violate the uniqueness? No. For any particular input, we can only have one output. We can have two different inputs that produce the same output, though, right? That doesn't violate the function rule. So this is 1/3 again. Okay. And then at 2, we're at 4 plus 2, that's 1/7. Huh? So it looks like it's going to be increasing in the neighborhood of -1 and 0. So in fact, it looks like we have symmetry here, right? So you might just guess from here. I think the maximum is going to occur, just from the numerical data here. We see a symmetry around -1/2, right? This halfway between -1 and 0. So what happens? What's v of -1/2? Well, what does the function do to its input? It squares, it takes the reciprocal, what you get when you square it, you add the input to that number, and then you add 1, right? So this is 1/4 minus 1/2 plus 1. And that is, well, this is -1/4 plus 1 is 3/4, and reciprocal of 3/4 is 4/3. Notice that that's bigger than 1, right? So in fact, v of -1/2 appears to be the maximum output. I'm going to prove that now. So this is a local max. Actually, it's a global max, but let's just call it. It is certainly local, right? So I'm going to say, look at v of x from a different point of view. This is a quadratic in the denominator. We're out of time, huh? So let me just do this quickly. What can you do with a quadratic? You can always complete the square. What happens when you complete the square here? Where are you going to get x plus 1/2 squared plus 3/4? Oops, sorry. Right, you square this out, you're going to get x squared plus x plus 1/4 plus 3/4 is 1. So you get back to here, right? Maybe convince yourself of this, right? But so that this term is always positive, it's a square. The smallest it can be is when it's 0, and that's when x equals -1/2. The square term is 0, and you got the reciprocal of 3/4, which is 4/3, and that's your maximum output. So this is always going to be less than or equal to 4/3 for all x. All right, so let's see. Do we have questions before we quit? I see there are some things in the chat. Yeah. Uh-huh. I don't have your glasses. Sorry, that's a private message, so not everybody can read it. No worries. Good. I appreciate your feedback. I really do. So I don't see any other questions there. So let me just point out that we do have these, where can I? We do have these homeworks, which, transformations, we're not ready to deal with those. So if you can work on 1 and 2 for now, and then, I have these out there, what are they? A lot of them you can probably work just based on your knowledge. The coordinate below represents the point 2, 5. Plot P, the image of P according to the transformation rule, X gets mapped to negative X. So that would be this point on the opposite side, right? You draw a dot, you submit that. Oh yeah, hey, I got the first one right. So yeah, so tomorrow we'll start talking about these transformations.
Excuse me, Professor.
Yeah.
I was wondering if you could post the class recording from yesterday.
Oh yeah, I haven't done that yet. Thanks for the reminder. Right.
Thank you.
We'll do. Okay, so this is actually kind of a difficult thing. So we'll spend some time on the transformation tomorrow. So it's like functions on functions, right? So when you take a function, you transform it. You're actually performing an operation on it. That's what a function does, right? Performs an operation on its input. What if the input to a function is another function? And what kind of things can we do? We can shift, we can stretch, we can shrink, we can reflect. Basically, that's it. All right. So I'll see you then, and I'll post up the materials.